Good day, everybody. I'm Gail Murphy from the University of British Columbia, and I am really pleased to be able to introduce today's keynote, and hopefully everything is going to be showing up great in the view that you're seeing. Hopefully you are seeing both Jeannette's slides and her picture, and if you aren't, let me know in the chat. Jeannette Wing has a very historic history, I guess, within computer science. She's done so many different things. Her PhD is from MIT, and she's been on faculty at the University of Southern California. She's been on faculty at Carnegie Mellon and is now the Avanesian's Director of Data Science Institute and a professor of computer science at Columbia. But that's not everything that Jeannette has done. She's also been an NSF director and also been a Microsoft vice president in charge of all of the Microsoft research labs around the world. So with this perspective and her background in formal methods and talks on computational learning and computational thinking, she's just really well poised to give us an idea about how we can use data for good. So over to you, Jeannette. We're really looking forward to your talk.
Thank you very much, Gail. And thank you to the organizers for inviting me to give this keynote. I am going to talk about data for good, ensuring the responsible use of data to benefit society. Let me start by talking about the data life cycle, which gives you a broader context of what data science is all about. It starts, of course, with the generation of data. We generate lots and lots of data. The scientific community has been generating data for decades now. If you think about large scientific instruments like the Large Hadron Collider or neutrino detectors in the South Pole and large satellites in the sky. What's obviously novel that makes data science so interesting and of fascination more recently is data about people. So we generate data, and it's the data that we're generating that is really pushing and advancing the field of data science. Now, of course, we generate a lot of data, then we collect this data, and we don't always collect all the data we generate. We process this data. By processing, I include everything from compression, encryption, but also the more mundane tasks of data cleaning and data wrangling. And we store this data in some medium. And we store the data in such a way that we can retrieve the data efficiently and effectively later. So we use data management techniques and database techniques for that. And then, of course, once we have the data, we want to analyze it to get some value out of it. And it's this analysis phase that is really causing the revolution in data science. And by that, I mean, of course, computational methods, statistical methods, machine learning methods, artificial intelligence, and so on. So this is why there's such great interest in data science today in academia and industry, by government, and so on. Now, it's not enough to analyze the data. We actually have to visualize the data. So we draw pictures to tell the story about the data. But it wasn't until I joined Columbia University and talked to my friends in the journalism school when I came to appreciate the phase that I call interpretation. Because it's not enough to visualize the data in terms of pie charts and bar charts and so on. One has to really explain to the end user, what am I supposed to see out of this visualization, or what am I supposed to get out of these probabilities or data distributions? And throughout the entire life cycle, we very much need, as a data science community, to think about the privacy and ethical concerns in collecting the data and analyzing the data, and of course, in telling stories about the data, especially if the stories are about people. So what is data science? I like to give this very succinct definition of data science. Data science is the study of extracting value from data. So the most important word in this definition is value. Value is subject to the interpretation of the end user. So it is, for instance, value to a scientist is discovering new knowledge, discovering a new exoplanet, for instance, with astronomical data. A value to a policymaker is actually allowing the policymaker to make data-driven decisions. And value to a business is easily calculable, it's bottom line. The second important word in this definition is extracting, because all of the phases that I showed in the previous slide is a lot of work. Each one is a lot of work, and there's a lot of work that is needed to actually extract the value that we have from raw data. So I want to share with you in a few slides a little bit about the mission and some of the activities that the Data Science Institute at Columbia has. The mission statement is a three-part mission statement, starting with advance the state-of-the-art in data science. This is about pushing the frontiers of research in data science. And at Columbia, the foundations of data science are, I think, almost uniquely defined, not just in terms of computer science and statistics, but also operations research, which is a very strong area that Columbia University has longstanding history in. The second part of my mission statement speaks to the full-fledged nature of Columbia, and that is to transform all fields, professions, and sectors through the application of data science. And finally, the last part of my mission statement is the title of my talk, and this is to ensure the responsible use of data to benefit society. To benefit society really means tackling societal grand challenges like climate and health and social justice. And responsible use of data speaks to the privacy and ethical concerns in the uses of data. So I summarized the three-part mission statement into three words: data for good, data to do good for society and for humanity, and using data in a good manner. The Data Science Institute of Columbia collaborates and works across the entire university. We collaborate with all 18 schools, colleges, and institutes, almost every department in arts and sciences and engineering, but also the medical campus, which itself has many schools, including public health and dental and nursing and so on. We focus on 5 areas: foundations of data science, as I mentioned already, health, social justice, business and finance, especially given that we're in New York City, and climate. We have 8 different centers and 3 working groups that are thematic, and they cut across all of the entire university, and you'll see some thematic centers that are not surprising, like smart cities or materials discovery analytics or education. And one program that we run is joint with Columbia Entrepreneurship, and it's unique in that we encourage faculty from across the campus in different disciplines to come together and co-design and co-teach courses where data science is one part of the course. And so one example is an undergraduate course co-taught by an applied math professor and a history professor. It's called Data, Past, Present, and Future, and it's a gentle introduction to data science. It is now actually on the list of courses that college students can take to satisfy their science requirement. Another example of a success story from this program is the Columbia Business School, where there's a 10-course sequence that teaches students data science. And now over 50% of the MBAs graduating from Columbia have some data science knowledge. The Data Science Institute also runs a very robust industry affiliates program. At any point in time, we have 20 to 25 companies who are members. And we have a larger relationship with IBM through this Columbia IBM Center on Blockchain and Data Transparency. So for the audience members who come from industry, we very much welcome your engagement with the Data Science Institute. So now what I wanted to do is walk through a few research stories in terms of what we do at Columbia in data science. And I'll just start with the one for advance the state of the art in data science. And the one I wanted to talk about is about multiple causal inference. And the reason I wanted to talk about causal inference is, as many people in the audience know, machine learning is only good at showing association or correlation, but not causality. But many fields like economics, political science, health, and social science want to infer causality, not just association. And so in this work, the Yixing Wang and David Bly look at the problem of multiple causal inference. Now, classical causal inference considers a single cause for an effect. For example, whether a subject receives a drug or a control. And this work I'm going to talk about considers multiple causes for an effect. For example, which genes affect a trait? How do sports players together affect how well a team is doing? How do all the various prices in a supermarket affect how much a customer spends? And it turns out that the multiple causal inference problem is an easier problem to solve with weaker assumptions than for classical causal inference. So let's consider a simple example. The scenario where I'm a movie director and I'm trying to decide which in my movie. I want to predict how much money my movie will make dependent on this cast of characters. The actors are the multiple causes and the revenue is the effect. In statistics, we might write this as trying to calculate the potential outcome. And in the Pearl-Do calculus, we would write that expression as shown. Now, the fundamental problem in causal inference is due to unobserved confounders. These are variables that affect both the causes and the effect. For example, the genre of a movie could be a confounder, as action movies make more money than artsy movies. Whether a movie is a sequel or not is a confounder. Some actors appearing together might generate more revenue than if only one were cast alone, and that's a confounder. So in classical causal inference, we start with an untestable assumption that we have identified all unobserved confounders. From this assumption, we can estimate the causal effects. Now, there is, as I mentioned, a significant untestable assumption in classical causal inference, and it's called strong ignorability. What this means is you think about all the confounders, and then you basically run a procedure that calculates the causal effects. But the first step is thinking about all the confounders. And so the assumption is that you've thought of all the confounders. So the strong ignorability assumption for a classical causal inference to work says there are no unobserved confounders. Well, the new idea is to construct what's called a deconfounder. And this idea exploits the multiplicity of causes to sidestep the search for all confounders. To construct a deconfounder, we build a factor model that captures the population distribution of known possible causes. And if we can build such a factor model, then we have essentially discovered a variable that captures all multiple cause confounders. So the deconfounder replaces an uncheckable search for all possible confounders with a checkable goal of building a good factor model of known possible causes. And this technique also has a weaker assumption than in the classical causal inference case. We just need to assume there is no unobserved single cause confounder. So back to the movies. In computing a deconfounder for the movies database, I discovered that without the deconfounder, Sean Connery's value is underestimated, and the values of the actors who play M and Q are overestimated. This makes intuitive sense, since very likely people went to see a 007 movie because of the draw of Sean Connery playing James Bond. So that was an example of pushing the state of the art in data science, where now there's a hotbed of activity in trying to bring together big data and causal inference. I want to now turn to the second part of my mission statement, which is to transform all fields, professions, and sectors through the application of data science. And what I wanted to do is just very, very quickly go through the different fields that have been embracing data science. So the first is an obvious one, because biology has been working with big data for decades. In this particular work, the researchers were looking at the microbiome around pancreatic tumor cells. And what they discovered was the microbiome was counteracting the effect of the chemotherapy treatment for the cancer. And that's not good. It basically means the chemotherapy was ineffective. But then what they then discovered is if you inject the tumor cells with an antibiotic, then that antibiotic would counter the effect of the microbiome, therefore making the chemotherapy treatment effective. In the next example, this work is looking at weak gravitational lensing imaging data. And so the astronomers who are interested in using convolutional neural networks to see if they can process the image data more effectively than, say, standard statistical techniques, discovered indeed that when comparing the networks, the convolution neural networks predictions with those that can be inferred from statistics, off-the-shelf statistical techniques, they found that the convolutional neural networks were better at predicting the parameters of the lambda cold dark matter model, which is used to try to understand the origin of the universe. In a completely different realm is work done by my colleagues looking at online marketplaces like Amazon Mechanical Turk. And this is really the combination of economics and machine learning coming together. This is something that I very much learned and appreciated when I was at Microsoft, where we had economists working with machine learning experts, and the combination of big data and, as I mentioned earlier, causality caused lots of very interesting techniques to come together. In this work on monopsonies, what my colleagues did is looked at the data in how online marketplaces behave, and showed that, in fact, these marketplaces behave more like monopsonies than, say, a fair market. A monopsony is where you have one buyer and multiple sellers. And whereas, say, a monopoly is where you have one seller and multiple buyers. So the fact that these online marketplaces acted in this particular way was a surprise to the economists. In a completely different example here, we're looking at finance, the financial engineering area, and robo-advising. So if you happen to have a lot of money, you might have a personal advisor, a human being, who over time, often years, learn your investor preferences. Well, obviously with a technique like reinforcement learning, you can actually learn someone's preferences in a matter of a few iterations of an algorithm. So this has been shown to be useful, and my colleagues are now actually trying to work with financial institutions to see if they can actually use this for robo-advising. In a completely different topic of history, or a different area of history, I have colleagues at Columbia in the history department who have amassed the largest declassified set of documents, and this is in the United States. And in this one example I want to explain, they looked at the cablegrams that the diplomats sent each other around the world in the 1970s. And what they wanted to do is, if they could, just by looking at the contents of the cablegrams, reverse engineer what the interesting historical events were in the 70s. And sure enough, they were able to, using topic modeling, distinguish between topics describing business as usual from those that deviate from such patterns. So you'll recognize, for instance, certain events like the evacuation of Saigon or the death of Mao Zedong. And another example of data science and political science, this is more relevant of recent history, because this app that I'm showing you here was actually used in the 2020 US elections. What these political scientists show is that doing friend-to-friend text nudging will get out the vote comparable to the gold standard in getting out the vote, which is door-to-door canvassing. So now I want to turn to data for good, responsible use of data. I have been promoting very recently a new research agenda, which I call Trustworthy AI. Very passionate about this new agenda. And it starts with my context, the context of trustworthy computing, where we have come to think of trustworthiness in computing systems to have properties like safety, security, privacy, reliability, availability, and usability. For trustworthy AI, they're brand new properties that all of a sudden we have to be concerned about. They, of course, include things like accuracy, robustness, fairness, transparency, accountability, interpretability, and even ethics. And so all of a sudden, AI systems are causing the entire computer science community and machine learning community and statistical community and data science more broadly to talk about these kinds of new properties. And for the work I'm going to explain today, I'm just going to look at one trade-off between robustness and fairness. This is work that was published in NeurIPS in last December. And we looked at the we looked at the problem of building a fair classifier that's not just fair, but also robust. We were motivated by looking at the COMPAS data, which many people might be familiar with, which is used in a risk assessment tool in US courts. And what we did was we took the COMPAS data and we built a fair classifier, and then we very slightly reweighted the data, and all of a sudden that fair classifier became unfair. In other words, it was not very robust. And so what we first determined was that state-of-the-art fair classifiers are not robust. And in order to build a robust fair classifier, we basically adapted an online algorithm, essentially a two-player game, to build a fair classifier that is robust to a class of distributions. So now let me talk a little bit about tackling societal grand challenges. And I'll start with some work in data science and agriculture. This is actually one of the reasons I like to tell the story is that it's not just about data, it's not just about agriculture, but it's also about climate change and policy making. And basically, my colleagues here looked at 5 different grains that are planted in India. And one should know that in India, the most prevalent grain planted is rice. And it's a chicken and egg sort of thing because the most prevalently eaten grain is rice. However, when they looked at climate effects that are to come, they basically determined that if India's crop production continues to homogenize towards rice, then food supply in the country may be more vulnerable to climate shocks. And these climate shocks are increasingly frequent. So these shocks might be droughts, they might be extreme heat, they might be changes to the monsoon seasons, and so on. So the point is, increasing the share of production contributed by other grains like millets and sorghum could improve the resilience of India's food production against climatic changes, especially these other grains' yields are actually comparable to the yields of rice. And so the point would be, once you have this data, once you have these observations, then you could go to the policymakers in government and say the government should encourage farmers to plant over the country more to provide more heterogeneity in the planting of grains over the entire country. The next example I wanted to show you is this incredible database or data set called Observational Health Data Sciences and Informatics. It's called Odyssey. It is a federated data set that is across 30 different countries. There are over 300 researchers involved in contributing to this federated data set. There are over 100 databases in this federated data set, but what's really, really impressive is that there are 600 million unique patient records that are accessible in this federated data set. 600 million EHRs. And because all of you are computer science or information technology experts, you will appreciate the fact that these 600 million records are all in the same format. And so when you have that large data set, you can start asking questions that you cannot fathom asking because if everything's in the same format, you can basically send a query and get the results back from that query, combine the results, and you have some interesting answers to your query. So let me give you 2 examples of what they were able to discover with just that data set. The way to read, and one reason I like to show this is to make the point that data is not good enough. I have to tell you a story about what you're looking at. These are very nice visualizations, but let me tell you how to read them. So first of all, they looked at 3 different diseases: diabetes, hypertension, and depression. And the way to read each circle of circles is each circle of circles represents a clinic in one of the contributing data sets. So for instance, the top middle one is the Columbia University Medical Center. And if you were treated for hypertension, you're basically in that circle of circles. And the way to read the circle of circles is that the inner circle represents the drug that was given to you first in a particular line of treatment. If the drug works, then fine. If not, you're given a second drug in your line of treatment, and that is represented by the second circle. And if that doesn't work, you're given a third drug, and so on and so forth. And the pictures only stop, the pictures stop at 4 in the line of treatment, but some of these radii go out for a long, long time, long space. So in any case, the 2 interesting results I wanted to share with you is one has to do with hypertension. And if I collapsed all the rings of circles representing all the data sets across the world in Odyssey, what would be observed is that 1/4 of the people in that data set treated for hypertension are treated uniquely. That's surprising. And what that means is that if you are in that 1/4, and I'm your doctor and you say, you know, Jeannette, who else in the world is being treated like me? The answer would be no one. The second interesting result has to do with looking at diabetes. And you'll see the top 2 rings of circles where the inner ring stands for this drug, the chartreuse stands for this drug, metformin. It turns out that for the most part, line of treatment and it works, except for the bottom circle, ring of circles. And you'll see that in fact, this particular data set represents a Japanese clinic. And it was only by looking at the observational data that one could see that something was different about the Japanese in treating diabetes. And it turns out that the Japanese are genetically disposed against metformin. So either the doctor tries metformin and it doesn't work, so another drug is given, or doctors know not even to try as the first line of treatment. So to wrap things back to my first story, the Deconfounder, I just wanted to say that once you have a data set like Odyssey and you have ideas like multiple causal inference, then you can start combining them and actually discovering interesting things. So the medical deconfounder basically takes the patient's medication records and lab tests and outputs the causal effects of all the medications in the Odyssey data set. And they looked at different diseases, including treatment effects for a cohort of diabetes patients. And what they discovered is that the medical deconfounder reduces false discoveries and identifies effective drugs that are more consistent with the medical literature. So I believe I'm out of time. Thank you very much, and I will stop sharing.
Jeannette, thank you so much for that wonderful talk. It was such a nice tour de the tableau of everything that's going on in data science. And so I would invite the audience to put questions into the chat. And I see that Bashar has already started us off. So let me ask that question. He says it's a very interesting talk on the role, opportunities, and challenges of using data in societally important domains. Can you give us your reflections on the implications for SE research and practice?
Okay, so yes, I know I'm speaking to a software engineering audience. I think speak about something that I've been thinking about even before I joined Columbia to run the Data Science Institute. And this is something that really hit me when I was at Microsoft. And that is the role of data. We have been so fixated on, if you will, writing code and making sure the code that we write does the right thing. There's like music playing. Okay, no more.
Yeah, I don't know why.
Okay. And I would say that, and a lot of the attention to the processes in software engineering have been in terms of building the systems with a lot of focus on the code we write. In the end, the tools we write analyze the code and help software engineers build their code, build their systems, test their systems, and so on and so forth. With data science, and especially with the rise of AI and machine learning, I think the software engineering community has to start looking at data as much as code. And that's one implication for software engineering research and practice, because who has the data? Industry has the data. Another really speaks to my interest that's coming out of the pursuit of trustworthy AI. Obviously, I've been thinking about, with my background in formal methods and verification, what can we say about how to say, verify an AI system satisfies a fairness property, a robustness property? And so I've actually been pushing the formal methods community. And by that, I would say the formal methods community is part of the software engineering community, pushing them to think, go beyond what we know how to do in currently in formal methods in industry or in academia, and think about these AI systems that are inherently probabilistic, that talk about data distributions and stochastic processes, and spit out output probabilities that are, in computer science, we're very comfortable working in the discrete domain, in discrete logic. Something's on or off, true or false, and so on. But in AI systems, it's inherently probabilistic. And so I think this is a challenge to all of us in the software engineering community in general. How do you even test even if you don't want to go the verification route? How do you even test these systems? What do people do today? And so I think there's huge challenges if we revisit kind of all of what we've been doing to perfect how to build large software systems to be reliable, where now data is as important a component in that software system.
Well, that's a great answer. We've got lots more questions in the chat, so let me try to find the ones that were coming in. Colin asks, he says he might have missed something as the video sometimes freezes when you're watching Clouder. In practice, how does the deconfounder capture all confounding factors?
It's the deconfounder is, so the way in which one constructs the deconfounder is through building something like a factor model. And then within that, there's essentially a discovery of a variable, say a latent variable, that has the effect of standing for all the confounders. Now, I'm simplifying it because I want to remind the audience that there is still this weaker assumption that you have discovered that there are no unobserved single confounders. But it's a weaker assumption because before, in classical causal inference, you had to assume that there were no unobserved confounders, period, all up. So it's interesting approach. It's a new idea. So I would encourage, but the reason I showed the very last example was to say these new ideas, and this idea came up about 2 years ago, these new ideas are applicable immediately to large data sets to already discover interesting, in fact, in this particular case, medical observations. So I would say, check it out.
And something definitely for people to follow up on. Patricia asks, there's obviously a lot of discussion that when you use data from the past to make decisions about the future, you might be replicating some of those past biases that are embedded in the data. So how can we learn from this past data and yet address fairness?
Yeah, so this is the canonical problem with all of the work that people are interested in with respect to fairness in machine learning, fairness in AI, and so on. So as Patricia says, the data that we're using to build these machine learned models are typically historical data. If there's bias in this historical data, then of course the machine learned model is going to reflect that bias, and therefore the decisions or predictions it makes is likely to be biased as well. This is, of course, the hot topic in trying to address this problem, and that's why there's a lot of interest in fairness in machine learning and debiasing algorithms and debiasing models and debiasing data. So the community is, in fact, trying to answer this question. What we're learning is, First, before I even go there, I should say that the community also recognizes that there are multiple notions of fairness. And so it just complicates matters. So for instance, in computer science, we all agree on what deadlock freedom means. There's no controversy. We know what it means. We can formally define it. We can actually prove certain protocols are deadlock free. So once and for all, we're done. We can build systems based on those protocols. In this world of data-driven computation, or models that we're building out of data, where all we have at our disposal is observational data. I mean, by definition, we don't have data that's not been seen before. Yet we want to build these machine learning models to work on data we haven't seen before. So we are in this odd situation, and so for fairness, for instance, there's a YouTube talk which many of you probably heard about, which is called 21 Notions of Fairness, and these are all formal definitions of fairness. So first and foremost, you have to choose a notion of fairness that you actually care about. The second is actually, I think it was like a 2011 paper, a beautiful paper that actually talks about fairness in machine learning and bias, and some 28 different notions of bias coming from the statistics community, the machine learning community, data science community, so on. So we are just all trying to figure this out. We all want the same, we all pretty much want the same thing, is that we don't want to build these models to be biased or unfair or unjust, given some notion of fairness. But it's still a challenge. It's still a challenge.
So let me ask a follow-up to that question. I mean, as we start to use more and more toolkits or libraries that embody some of these models, right, that we feed them data, do you think that we'll eventually get to the place where we'll be able to express the fairness we're interested in assessing, or somehow be able to tune parameters that allow us to understand?
Already, so of course the big tech companies have already acknowledged that even some of the, tools they put out that and data sets that they put out and make available for researchers can potentially lead people to build unfair models and so on. So they actually have services, that fairness checkers, if you will. It's all modulo, some notion of fairness or some constraints, like you have to use TensorFlow, whatever it is. But I think that is exactly, this is why there's a lot of research in this area, because we are making progress. Do I think that we'll eventually get to the point where, you select on your menu, your fairness option, you upload your data set, you upload your machine learning model, you press a button and out comes fair, unfair? That's a dream. That's what it would be nice that we could do. And then actually what's more important is, if something says it's unfair, then what should we change? Should we go back to collecting more data? Should we change the algorithm in some way? Et cetera, et cetera. So this is my grand vision of actually part of addressing trustworthy AI, to build such a platform where one could do that.
I think you're getting lots of applause for that answer, and people that are probably willing to join in. We have about 2.5 minutes left, and we have a big question from Puyan. So maybe I'll ask that, and that might end up closing out our session, but I'll remind the audience that you can continue in the discussion room afterwards. Puyan says, thanks for the insightful talk. Could you elaborate on the results you showed that with a causal inference, you could learn a more robust and fairer model? Is it the case that with causal inference, you could learn about the causal mechanism, and through which you could learn a more generalizable model, and therefore the model might become more robust?
This is kind of like a research question in my mind. So first of all, you're really pushing the community, if you will, by throwing in the words causality, robustness, and fairness. I showed you a little teeny weeny result that showed you how to build a fair model that's actually robust. Now you're throwing in causality and so on. So this is state of the art, what I have been able to show, but it's an excellent question. And there's something tantalizing about the relationships. First of all, there's something tantalizing about the relationships among properties that I mentioned, like accuracy, robustness, fairness. You mentioned generalizability, and it's drawing from all the communities like optimization and operations research and computer science and statistics and machine learning and AI and whatnot. Now, on top of that, you want causal inference, and we don't know all the relationships. But the intuition that you are suggesting, I think, is valid. And there's something that, all I can say is there's something tantalizing, interesting about these properties. We don't exactly know formally all the relationships among them. We're still, what's interesting is the properties have divided the community, the robustness community, the fairness community. And I'm actually saying these communities actually have to talk to each other because their techniques may be able to help each other. And now you've added the causal inference community. So it's an excellent question.
Thank you so much, Jeannette. We're about to go off